So the goal of this assessment is to identify the key features of quadratic equations, graphs, and tables. Using both graphs and tables, I will explain why these patterns make sense mathematically.
On a Saturday night in the summer, sundown and they all come out. Lamborghinis and they rented hummus. The party's on, so they're heading downtown. Everybody's looking for a come up.
Let's start out discussing what makes an equation quadratic, and some key features to help us distinguish these characteristics. For equations, we want to look at whether a variable is squared or is raised to the second power. It's also called equation of degree 2, to help better explain it. On the topic of raising to the second power, squaring would be considered the highest power in the equation, and in that sense, it can cause an equation to be quadratic. Some examples of an equation that makes it quadratic include y equals x squared. The variable seen here is being squared and is raised to the second power. A second example is y equals x squared plus 3x equals 1. The variable is once more being squared, raising it to the second power like shown in example 1. Another example of a quadratic equation also includes y equals 3x parentheses x plus 6. In this example, two x's are being multiplied, which in result makes this equation quadratic. Most equations that are quadratic usually get away with a variable being squared, and a variable being squared alone for it to be considered quadratic. Now that we have a general idea as to what a quadratic equation can be summed up as, let's take a look at some examples of equations that are not quadratic. An example of an equation that is not quadratic involves y equals 2 to the x power. This equation is not quadratic for the reason that you cannot flip the process of a variable being squared to having it be squaring a variable. Another example is y equals x to the fourth power plus 2x to the third power negative 5x to the second power plus 2. Having x to the fourth power and x to the 3 power makes this not quadratic because you are no longer squaring or to the second power, which is what it takes for an equation to be quadratic. Even if there is one variable being squared in that equation, x to the fourth power and x to the third power automatically make this equation not quadratic because the highest power is greater than 2. A final example of an equation not fitting the quadratic requirements include y equals 1 divided by x squared. Unfortunately, any division of a variable that shows up in an equation is automatically not quadratic.
Even though we both know we're liars and we start each other's fires, we just know that we'll be alright. Even though we
Now that we have covered some examples of quadratic equations and non-quadratic equations, it's time to bring up some key features of graphs that make it quadratic. Some key features to note when reassuring yourself if a graph is quadratic include symmetry over a vertical line, having the U-shape on a graph open up or down, exactly one turning point, and making sure to keep an eye out for only curves in a quadratic graph. For instance, no straight lines. Some examples of quadratic graphs include this graph. The graph opens up and demonstrates exactly one turning point on the vertex, along with showing symmetry over a vertical axis. As for the second graph, this one opens down, shows one turning point on the vertex, and displays symmetry over the y-axis. This one demonstrates similar qualities and shows the graph opens up. It shows one turning point on the vertex and once more passes the vertical line test. This symmetry, or U-shape, makes sense mathematically because a U-shaped curve, also known as a parabola, allows the vertex and the axis of symmetry to be counted for by using the formula for the x-coordinate of the vertex. Without the U-shaped graph, there can't be an axis of symmetry without breaking the quadratic rules that make a function quadratic. Some examples of graphs that are not quadratic include this one. This example of the graph is not quadratic because there are more than one curve and there is no symmetry over the y-axis. This one is not quadratic because there is no curve as well as no symmetry over the y-axis. As for this one, the graph shows to not be quadratic because there is a series of curves as well as more than one turning point. Moving forward to our last subject of quadratic functions, tables, Here are a few key features to hint when finding if a table is quadratic or not. If the difference is not constant, but the second of differences are constant, the graph is quadratic. Another example is tables that show symmetry in y values. An example of a quadratic table is this one. This graph is quadratic because it shows the second difference, that is, the differences that have the same value. In this table, you see the same number under the difference of differences, which shows it is quadratic. The next table depicts similar characteristics in contrast to the same numbers under difference of differences. For this one, it is ending in 3. This table proves that a table can be quadratic even with ratios. This table also shows that it is an exponential function. A non-example of a quadratic table is this one. The table shows the second difference in numbers that is not consistent, as a quadratic table should be. Similarly enough, so does the next table. This was all for today on identifying a quadratic function. I hope that this video helped to better magnify your understanding of identifying the key features of quadratic equations, graphs, and tables. Thank you so much for watching.
You're my gospel, but I'm losing faith.